Extending Time Between Overhauls for Helicopter Main Gearboxes by Jeffrey Morales. Introduction. The helicopter main gearbox is an essential and complex component of the aircraft. A periodic inspection of the component requires a teardown and overhaul procedure. The time between overhaul is calculated by the OEM, original equipment manufacturer, using statistical regression modeling and MGB run stand data. The prescribed method has been accepted by the Federal Aviation Administration per AC 29 MG15. Here is the helicopter main gearbox. It is a complex piece of machinery with many gears and bearings. It is an essential part of the helicopter. As you can see, there is many different attachments attached to the helicopter gearbox in order to make the helicopter fly. This is regression modeling. This is when the OEM takes a weighted factor of wear to prognosticate when an actual gearbox will need to be overhauled. Regression modeling is just simple statistical data with weighted factors. This, coupled with transmission run stand data, is where they verify their TBO time. The problem statement. The problem is that this method has determined the TBO time of the helicopter MGB is antiquated. It's not the most accurate way in determining TBO time for the MGB. A new method is needed in order to extend the TBO time past what the OEM has prescribed using a more updated method. The new method being proposed by this project, the new method utilizes HUMS, MGB run stand data, periodic oil sampling, and fault seed testing on the MGB. Using these different techniques, a more accurate TBO time may be calculated, and one that could extend the TBO time past the OEM's recommended TBO time. The TBO. Typical TBO for an MGB is 4,800 flight hours. The TBO requires extensive downtime to complete and can be very expensive. Labor costs are high because the inspection can only be performed by qualified personnel. Extending the TBO time could save the operators in both time and money. Here is a maintenance manual of an aircraft, an A119. This Augusta-Westland transmission is prescribed to be overhauled at the 4,800 flight hour interval, with the 60-hour flight over, meaning that the helicopter can fly another 60 hours on top of the 4,800 hours if needed. HUMS monitors helicopters' MGBs using accelerometers to measure vibration thresholds. HUMS data can be collected and compiled over the life cycle of the MGB. HUMS data can be used to determine when the MGB could fail using track and trend analysis of the compiled data. HUMS data alone is not considered sufficient data to determine TBO by the FAA AC-23 MG15, but HUMS data coupled with other techniques may be enough proof to extend the TBO time. Here we see a helicopter main gearbox outfitted with accelerometers. The accelerometers are strategically placed throughout the MGB for the most critical bearings and gears. A tachometer is also inside the MGB for the engineers could know the speed of the MGB while the aircraft was running. This speed is critical because it allows the engineers to understand what modes of flight the MGB was in. Here we find HUMS trend analysis. HUMS trends analysis uses megahertz. This megahertz tracks the trend of the actual MGB. As you can see, above acceptable threshold is 51.5 megahertz. And as you can see, the transmission with track and trend analysis doesn't go above that threshold until the 10,500 flight hour mark. And here, the line is where the actual OEM's prescribed TBO time is, which is 4,800 hours. Periodic oil sampling. Periodic oil sampling can be used on the MGB as a means of tangible information to contrast with the HUMS data. The parts per million of the metal content in the oil of the MGB can be established during the first initial runs of the helicopter's MGB. The periodic oil sampling can continued over the life of the MGB. The periodic oil sampling can be used to determine the internal health of the MGB. The oil sampling can provide enough evidence to the FAA to extend a TBO time past the OEM's prescribed time. The FAA approves the oil sampling method to extend TBO on aircraft engines per AC 120-113. Here we see a chart with the parts per million of the metal content of the MGB. At every 150 flight hours, a periodic oil sample can be taken. This oil sample can be tracked and trended as well, and also contrasted to the HUMS data to see if there's any fluctuations or abnormalities. Any abnormalities would be called for an transmission inspection. But if there is no abnormalities and the track and trend analysis stays the status quo, the gearbox can keep flying past the prescribed OEM's time. The MGB can can run the MGB in a variety of different states of flight. The run stand can be fitted with HUMS sensors and be able to pick up any abnormal vibrations while the MGB is running on the test stand. The MGB can also be fitted with damaged components to use on fault seating test. The HUMS should be able to detect the failed components in the MGB by analyzing the abnormal vibrations in the MGB. The HUMS data can track and trend the abnormal vibration and prognosticate when the MGB will fail. The type of analysis is needed to validate the HUMS data of the MGB in order to be accepted by the FAA. Here is a basic MGB test stand. A dynometer will read the output of the transmission. A speed gearbox will actually increase the speed of the gearbox, and a DC motor. The DC motor will be used to run the gearbox in a variety of different flight profiles. Here we see a gear that has been seated. This is a minor defect and a major defect. With the evidence in A, an abnormality, track and trend will be checked per the HUMS data on the test stand. With the major defect, it'll also be done in the same way. Both HUMS sensors will be able to analyze the difference between a minor defect and a major defect, and will go along with the rest of the data on the MGB run stand. This, combined with the HUMS data and the periodic oil sampling, can be used to verify the internal health of any gearbox fleet-wide. The project proposes a strategy to better predict TBO times by using HUMS data, periodic oil sampling, and fault-seating MGB run stand data. The new strategy can provide a more modern approach to determining TBO times for the helicopter MGB by using the methods prescribed in this paper. The core program outcomes. Aviation maintenance. The student will be able to demonstrate an understanding and application of the fundamentals of aviation maintenance, commonly accepted maintenance practices, and global regulations applicable to the aviation maintenance industry. In order to develop the solution for this problem, a careful study of what is needed to be done to receive TBO validation was needed. Understanding the current FAA regulations regarding TBO times and the sufficient data needed for the validation, this process required lengthy knowledge of the FAA regulations. The project also required a complete working knowledge of how HUMS works and the latest in HUMS technology. Reading FAA documents AC-29MG15 and AC-120-113 provide this project with methods that can be used to determine TBO time for helicopter MGBs. Aircraft maintenance management. The student will be able to demonstrate an understanding and application of management functions applicable to the aviation maintenance operation for all types of aerial vehicles. The operators would benefit from the extension of TBO time for helicopters MGB. The cost of doing an extensive overhaul is expensive, and operators can also lose money with the excessive downtime associated with the inspection. The maintenance managers and operators could benefit from the strategy proposed by being able to extend the life of the MGB and predict MGB health. This strategy would aid managers in forecasting downtimes and help transition them to a more condition-based maintenance program. Aviation maintenance safety. The student will be able to demonstrate a comprehension of and application of the basic concepts of ground and flight safety pertaining to the aviation maintenance industry. When the use of HUMS monitoring systems, the aviation industry has received an extra layer of protection when it comes to aircraft health. HUMS is able to prognosticate when failures can happen with components and also evaluate the component in real time. The kind of monitoring of components has increased the safety of the aviation industry, as well as enhanced maintainers' awareness of any critical faults of the aircraft. SWOT analysis. So this would be the strengths internal. The strategy provided in the project for determining TBO time relies on proven technology used throughout the aviation industry. The strategy uses HUMS information sources that can be contrasted against fleet-wide HUMS data, giving a bigger data set. Using periodic oil sampling coupled with HUMS data provides information on the internal health of MGB while monitoring any abnormal vibrations that are present outside the MGB. Internal weaknesses. The use of HUMS has a cost associated with in terms of analysts required to look over the extensive HUMS database. Periodic oil sampling will also cost the operator in terms of extra maintenance and the associated cost of analyzing the oil sample. The rigorous testing of MGBs has to be factored in correctly, or else the prognostication will become skewed. Tests must be overanalyzed to ensure correct trend analysis is calculated. External opportunities. The use of the proposal could lead to more condition-based maintenance program, where components are taken offline and on a condition basis only. On-condition basis only. This proposal could benefit the supply chain as well, utilizing HUMS data to track trends and identify components needed replacement and placing orders prior to failure. This could lessen lead times for components as well. The proposal also could aid in implementing the just-in-time or JIT strategy. The monitoring of the components will be used to forecast parts and services on an as-needed basis. The strategy will allow for operators to carry very little stock because components are monitored in real time and can be scheduled for replacement instead of being replaced on condition. External threats. The HUMS data can be corrupted from the data transferred from the aircraft to the maintainer, causing the data to be erased or damaged. Servers that load data of HUMS for fleet-wide analysis could be hacked with malicious intent or could crash, causing a system-wide deletion of data. Fault-seeded analysis may not take into account the environmental or human factor effect associated with the MGB and may not be accurate enough to prognosticate decay in the MGB. This is my project. Thank you.